This lesson deals with supplemental problem 8.10. You can find this problem in the ECE202 ebook in the Chapter 8 supplemental problem starting on page 9. Given this series RLC circuit, could you determine the resonant frequency? Suppose that the input is a line voltage, which would have a magnitude of around 170 volts at a frequency of 60 hertz. Suppose this is a 10 ohm resistor and a 10 microfarad capacitor. Could you solve for the value of L to put this circuit at resonance at 60 hertz? And then could you solve for the current I sub S, V sub L, V sub C, and the voltage across L and C in steady state? We'll again use our three-step algorithm. Before we do that, let's determine the resonant frequency. Resonant frequency is determined by finding the impedance seen by the source and setting the imaginary part equal to 0. What's that going to be equal to? Well, I've got a resistor whose impedance is R, an inductance whose impedance is j omega L, and a capacitance whose impedance is minus j over omega C. So the series combination is going to add those three things together. Let's put together the imaginary terms of omega L and minus 1 over omega C. So I have some R equivalent and I have some X equivalent. Because of the sign differences here, I could set this equal to 0. That's going to occur at one frequency, so let's call that frequency omega naught. So then omega naught times L minus 1 over omega naught times C would be equal to 0. We're going to solve for omega naught. Put this on the other side of the equation. Bring the omega naught over here and the L over here. So I get omega naught squared is equal to 1 over LC. So then omega naught is 1 over the square root of LC, and then divide by 2 pi, and you've got the resonant frequency in hertz. And now to solve for the value of L needed to put this circuit at resonance, use that formula. So I've got 2 pi times 60 is my resonant frequency. That would equal to 1 over square root of LC, where C was equal to 10 microfarads. Let's square both sides of the equation, and let's solve for L. So when we square this, we'll have 1 over L times 10 microfarads. Bring the L over here, and bring the 2 pi 60 squared over here. And that turns out to be 703.62 millihenries. This is not a standard value, but suppose I could get exactly that value. There are variable inductors, and we could actually tune it to that value. So let's do our three-step algorithm. Our source then is 170 at angle 0, 10 ohm resistance, and then j omega L, and 377 is 60 times 2 pi, times our 0.70362, and that gives me j 265.3. Now the impedance of the capacitor is minus j over omega C, that was 377 and 10 microfarads. That turns out to be minus j 265.3. Again, what's going to happen here is this is going to cancel. Let's solve for the current in this loop. It's going to be the voltage divided by the total impedance. So 170 at angle 0 divided by 10 plus j 265.3 minus j 265.3. These are going to cancel each other. I'm left with 10. So I'll get 17 amps at angle 0. That's actually a lot of current. The current's going to flow in the inductance and the capacitance, so we can calculate their voltage drops by just Ohm's law. So for the capacitor, we've got minus j 265.3 for the impedance and times the current. The current was 17 at angle 0. Of course, this is the 265.3 at angle minus 90. That's going to give me 4,510 volts at angle minus 90. For the inductor, I've got I sub S times j omega L. That's 17 at angle 0 times 265.3 at angle 90. And that too is 4,510 volts at angle 90 degrees. Now if you add these two up, in other words, the drop across here and the drop across here, you get this plus this. Let's put that into rectangular form. So this is going to be equal to minus j 4,510. This is going to be plus j 4,510. You get 0 volts. So the drop across here is equal to 0. And again, it's because these two impedances cancel each other. But they create very large voltages. So even though the voltage here is ideally 0, the voltage here is huge, and the voltage here is huge. Now they're out of phase with each other by 180 degrees, but they're still a very large voltage. Now let's do step 3. Now let's put this back in the time domain. 17 at angle 0, so 17 times the cosine of omega t. Just putting that between the magnitude and the angle. Units would be amps. Our capacitor voltage, though, is 4.51 K. Engineering notation. Put the cosine of omega t between the magnitude and the angle. And again, that would be in units of volts. The voltage across the inductance would be the same value, but the angle is plus 90. And the voltage across this series combination is 0. In this particular example, R equivalent was not a function of frequency. So the maximum current occurred when the denominator calculation of Z equivalent was its smallest value. And that occurred at the resonant frequency. This is one of only two circuits that you get the actual maximum value of a voltage or current at a resonant point. Usually we have it somewhere off of the actual resonant point, as we saw an example in the lecture notes of Chapter 8. Again, what's interesting here is that the voltage across the series combination is 0, but the value across the L and C is not 0. In fact, it's very large, just simply out of phase with each other. And this is supplemental problem 8.10.